Okay, so today we're going to go on with 1D mechanics. I'm going to spend most of the class on MATLAB integration. I'm going to do live coding in front of you. I'll make mistakes and you'll fix them, and we'll get a nice plot at the end of it. First, I want to start with a quiz. The quiz goes like this. We're learning the laws of mechanics, which are linear and angular momentum balance, and we're going to make predictions with these laws. And as engineers, if we take a real problem, there will sometimes be errors in our results, and we can attribute some of these errors to the fact that the laws of mechanics are only approximations and have been overthrown by quantum mechanics, special relativity, general relativity, string theory, and so on. So there's some errors in our calculations which will be due to the fact that mechanics calculations we're learning in this class are only approximations. The question is, A, B, C, D, or E, how much of our error can we account for by the fact that the laws of mechanics are only approximate? Okay, you have 5 seconds more to vote. 1, 2, 3, 4, 5. We lock up the vote. We look at how you did. I hope we look at how you did. Okay, so the answer is, as best I know, E. We will make lots of mistakes in your life, but if you want to blame them on the laws of mechanics and that special relativity and general relativity and quantum mechanics have thrown them out, you can only account for about a 10 millionth of 1% of your error that way. Okay, so now somehow I've got to say what the right answer is here. If you do very extreme calculations, it might be that you could get down to D. It would be very extreme situations where you'd have errors of 1 part in 10 to the 7th. And A, B, and C are just totally wrong. Okay, now let's try again. When you do mechanics calculations, there are errors because you don't know the material properties of things. How much of your error can you account for by errors in material properties, approximately? A, B, C, D, or E? Ten seconds left. 9, 8, 7, 6, 5, 4, 3, 2, 1. We're going to lock up that vote. And we look at the result, I hope. Okay, so the answer is a little bit ambiguous. It depends on what material properties we're talking about. If you do a very careful experiment with, say, the modulus of quartz or something like that, it can be 10 to the minus 3, 10 to the minus 4. If you're doing experiments that involve friction, things like that, it's more like 10 to the minus 1. And if you're ever in this situation, you're in a very, very special, accurate situation where you know some material property this accurately. So it would only be, material properties are only known this much if you're very lucky, this much if you're dealing with things like coefficient of friction, drag coefficients, coefficients of restitution, things like this. The only time you get accuracy like this is for, say, elastic modulus. Not for yield stress. Yield stress and so on, you're down over here again. Okay, so A and maybe B are the right answers, but definitely not C, D, or E. Okay, any questions about these quiz questions? Any questions about the logistics of the course? Yes? The homework assignments go into the basement of Upson. You've got to know your TA's name and section number to know which box to put them in. I think it's approximately across from the candy machines. Is that correct? Yeah. Near the computer lab. Any other questions about logistics in the course? Okay. How about the homework due date and time? I tried to pick for maximum convenience for you. And this is based on my sense of when homeworks and other classes are due, which I think are Thursday. Most of you are in 225 and 212, and I will try to, some of those courses are inflexible, and when they have big workloads, and I will try to take that into account a little bit. So homework due time is one of those things. Does anybody want the homework due a different day or time? Okay. So now we're doing 1D mechanics. What do we mean by 1D mechanics is we have one spatial dimension and also only one degree of freedom. Only one number is required to specify what the configuration of the system is. X is a good variable. Y would be a good variable. S, you can use whatever variable you want. And we're going to keep track of the position of some mass. And this mass will have some force on it. And the general case is that the force is given as a function of position, velocity, and time. So if you know this function, then we can write the equation F is equal to ma. We can invert that equation, and it turns into A equals F over m. Supposedly, we know what this mass is, and we also can rewrite this equation as V dot is equal to F over m, and we can couple that with the equation X dot equals V, and these become the governing equations for the system. And this is the crystal ball view of things. If we know what the force is as a function of the current state, then we know how the state is going to evolve in time. The velocity is going to change like this, and the position is going to change like this. Now, if we want to think about this numerically, so we really have the crystal ball viewpoint, we say that the new value of the velocity is equal to the old value plus the acceleration times delta t. And we say that the new value of the position is equal to the old value plus the velocity times delta t. And this is how you think about the crystal ball that you can predict the future. Now, what are examples of this function? Okay, well, the simplest example, I'm just going to give a long list of examples. The simplest example is F is equal to 0. That's a famous example. So famous that there's a whole law named after it, which is Newton's, after all these years I should know, it's Newton's first, second, or third law, I don't remember which one. And the law is an object in motion tends to stay in motion unless acted upon by a force. So here it is, not acted upon by a force. That's all that law is about, is that special case. And this tells us that the acceleration is equal to 0, which tells us then that the velocity is equal to constant. And that's an object in motion, dot, 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 tends, dot, dot, dot. So that's famous example, F equals 0. Then if you want to go to your high school physics, we could have F is equal to F0 is equal to a constant. Then that tells us that the acceleration is equal to some constant, which is F0 over m. And it says that the velocity is equal to the initial velocity plus a0t. And it says that the position is equal to the initial position plus the initial speed times t plus a0t squared over 2. That's your famous high school physics example, physics 1. And based on those two formulas, you can write 20 different problems about giving the time, giving the position, initial position, final position, average speed, and so on. And you did 1 million problems like that in high school or freshman physics just based on this one special example. Another special example is that F is equal to, say, minus CV. And this is what is called viscous drag. And this is a simpler version of the problem I did in lecture the past 2 times, because there's no gravity here. So you just have something shot into honey, but there's no gravity pulling it down or sideways or anything. And from this, we get that the V dot is equal to F divided by m, which is minus c over mv. So then that implies that the velocity is equal to v0 e to the minus c over mt. And this is this exponential decay. So the motion is damped. And then we could integrate one more time to get the position, which I'm going to skip. Similar example is the example you have for homework now, which is this gross example, which is force is minus c v absolute value of v. And by this v absolute value of v, this stands for v squared, but it's keeping care to get the signs right, so the drag is in the right direction in both directions of motion. And this is quadratic drag, and you have a homework problem, which is apropos of the news. Just about 100 yards from here last night, someone was shot. Just over here, about 100 or 200 yards. And shot in the buttocks. As the bullet penetrated the flesh, the main resistance to the bullet's motion was the fact that you were mostly made of water, and so the bullet slowed due to quadratic drag, and you can calculate then approximately the penetration of the bullet into the flesh. 1:30 this morning. Another example is that force is given by some function of time, and an example of that would be, say, a cosine of t. So we have, say, an oscillating force on something, and when you have an oscillating force, you get an oscillating acceleration, and this gives, therefore, that the velocity as a function of time also oscillates, plus a constant, so the velocity as a function of time will look something like this. Perhaps the most famous example is where the force is equal to minus kx. And this one has a whole special name. A friend of mine once, a physicist, said there are only 3 examples in physics, and I forget what the other 2, but this is one of them. It's like this example comes up again and again and again. All parts of physics, all parts of statics even, is hidden. A very important equation. Okay, so who just raise your hand if you think you recognize that equation. Raise your hand if you don't. Okay, so how does this equation work? I give you a cartoon of it. From the cartoon, you can remember what the solution of the differential equation is. Let's say this is 0. I'm the mass, and there's a force on me. If I'm over here, there's a force in that direction of minus kx that pushes me back. If I'm over here, there's a force in that direction of k. Well, it's k times negative k times negative x gives a forward force in that direction. And if I'm right here, there's no force on me. So if I start the system right here, where does it end? Okay, I'm going to give you a very graphic, dynamic visualization of this system. Ready? Go. Okay, so that was it. It's not very interesting because if I'm starting at 0, there's no force, nothing gets it going. The crystal ball tells us going in the future, nothing happens. On the other hand, if I start over here, there's a force on me in that direction of minus kx. I have an acceleration. If I don't pay attention to the fact that the x is changing much, I accelerate in a quadratic way according to distance equals 1/2 at squared. That's what it looks like. I go faster and faster, but not as much as you would think, because when I get over to here, I'm not accelerating anymore. So what happens? Let me start farther away. I start here, go. Faster and faster I get to here, then I start to slow down, then the force pulls me that way until eventually I come to a stop. I accelerate that way. My speed is roughly constant here. I'm neither accelerating nor decelerating. Right at this point, my acceleration is 0, but I have some velocity, so I keep going that way and back and forth. Now, why does it work out that these oscillations have constant amplitude? From that intuition, you can't know that directly. All you see is that when I'm over here, I accelerate that way. When I'm over there, I accelerate that way. How does it exactly work out that the amplitude is constant? Well, that follows, say, from conservation of energy, which you can derive. But the intuition gives you about the right answer. So what we know from this is that x of t is some kind of cosine function of t plus some kind of sine function of t. You can't tell the difference. Both of these are called sine waves. It depends on when you start time or what the initial conditions are. For example, if I start here at rest, then it's clearly cosine as a function of t, whereas if I start here with some velocity, it's a sine function of t, and I can do some mixture of the two. So there's some unknown constants here. On the other hand, there's a coefficient in this. Well, the bigger the spring constant, the faster I oscillate. The bigger the mass, the slower I oscillate. The bigger the spring constant, the smaller the mass. And the math makes it work out that actually we need a square root in here. Or if you just check the units, you'll see that you need a square root there. Should you know how to derive that equation? Probably you should. Should you know that solution? Absolutely. So if you go to the appendix of the book, it has a list of differential equations, all of which you should just know cold within the next couple of weeks. What does it mean to know it? It means you look at it and you just know the solution. Does that mean memorize it? Well, that's like saying you should know what your name is. Should you memorize it? It's more than that. You should know it. Okay, it should feel right to you lots of different ways. Okay, so now what I'd like to do is do this on the computer. But before that, I want to give you a demo of a pretty good spring and mass. This is better than you will find in engineering practice. Now, in engineering practice, how does it really work? The way it really works is that almost all things are kind of springy. And almost all things have mass. So almost all things vibrate a little bit. And then the model of that vibration is a spring and mass. Here's an extremely ideal case, which is not really important in most engineering applications, but it shows you very precisely how things work. So it's going to be very noisy, but here's how it goes. So here it is starting at 0. I started over here, it accelerates that to the left. I started over here, it accelerates to your right. And I let this go, it does this oscillation. And it has approximately constant amplitude. Let me see if I can get my hand in some fixed place. So it just comes and kisses my fingernail almost every time because the friction is so low. Why is that? There's little holes here with air coming out. So this is sliding on a film of air which has very low resistance compared to the friction of the aluminum on aluminum. And this one is so precise that if we put in the numbers and the spring constants, we'd get about the right answer. They very carefully told me the masses and the spring constants here so I could do the calculation, except they didn't tell me the units. So I'm going to yell at somebody. Okay, so now we want to do this on the computer, and that's what I'm going to do for the rest of the lecture. I'm going to try and use this idea to be able to figure out what the motion is of all of these different systems. Any questions before I do that? Yes?
For your graph of 8.19, you have a positive acceleration per bit and then a negative acceleration per bit. Why wouldn't the speed go back down to 0 after you go through every one full sine wave?
The speed does go to 0. So what happens is if I start here, I start with the speed of 0. I accelerate, go faster and faster, slower and slower, and the speed is 0 here again. Then I go faster and faster. I'm at a maximum speed in the middle, slower and slower, and then the speed is 0 here again. So if you look at these sine waves, the position is oscillating, and at the top and bottom of each of those oscillations, the velocity is 0.
Then why is the velocity graph you have the 1, 0, 0, 8.19?
Because this is the previous example. That goes with this one.
Right.
Oh, why is this like this? This is the acceleration is oscillating, but I didn't say what the initial condition was. So any solution I get, I can superpose a constant velocity solution to it, and it's still a solution. So naturally, you think of it like this, but if we just do one like this, we'll get this. In fact, why don't we remember that one and do that on the computer and see how it goes. Okay, so now I want to get the computer to work. I'm going to try and turn on this touch screen to begin. Laptop computer, center screen, large center screen lower. Lights. Okay. Here we have two choices for projection. One choice is the way it is now, and the other choice is like this. there's light and dark. Are you ready? All in favor of light, raise your hands. All in favor of dark, raise your hands. Okay, dark it is. Okay, so I just turned on MATLAB. So this is initial MATLAB right at the beginning. I'm going to start doing some example. So I find the folder associated with this class, which is somewhere down here, 00, I think I called it 2030. Here it is, 00, 2030, Spring 213. I'm going to start and do a new, I think I'll call it a new script, which means I'm going to just start editing a new script file. In general, unless you're doing something very short, I recommend you don't use the command window. You can do advanced calculations like this in the command window, but I recommend you do them over here. And why do you do them over here instead of in the command window is, if you can manage it. What's happening is my mouse is drifting on this slope. Okay, I can go over here and then I can run it. I've got to say what's the name of this. This is going to be test 2. What was test 1? That was when I made sure I could do this lecture. Test2.m, and I get my result 4. And see, this way it's really good because I didn't want to do 2 plus 3. I actually wanted to do 2 plus 3. Sorry. And then I can run it and get my answer and not have to change everything. So it works much better if you use the script window. Okay, so our goal here is to be able to find 1 degree of freedom motion in 1D. I'm going to post what I do here, so if it's easier for you to pay attention without taking notes, you can do that, but it's fine if you want to take notes. So what's the basic idea is, you see my mouse drifting down it. The basic idea is that I'm going to say, if I know the current position of x, and I add to it the velocity now, and multiply it by the time step, which I'll call h, from that I can get the new value of x. That's my basic idea that I'm going to be using again and again. And I have that for x, but I have the same idea for velocity. If I know the old value of the velocity, and I add to that the acceleration times h, that gives me the new value. And in general, I want to tell MATLAB to think about things, but just keep its thoughts to itself for a while, and then after it's figured it out, give me the answer. So I put a semicolon after most lines there. Okay, so this is the basic idea which we're going to be using for integration of differential equations for all time. Yes? H, I'm going to use h. Well, I'm going to have to define it somewhere anyway, right? So I'm going to say h is 0.1, which is not really answering your question. What do I mean by h? Is h is equal to what I want to think of as delta t, is how far in the future I'm going to calculate things. But I'm going to have to calculate all these different, this is the core of the calculation. This is how the crystal ball works, is right here. But I'm going to have to put a bunch of stuff around here to make this crystal ball work, because I don't know what h is. Okay, I know that. But I don't know what the old velocity and the old acceleration is. Okay, so I've got some old velocity, some old acceleration. I'm going to have to figure that out. So somehow coming into this, I'm going to have some old one. But my old one is going to be the old new one, because I'm going to do this again and again. So I have to say, somewhere I'm going to have to say, oh, the new one is the old one, and the new value of the velocity is the old value of the velocity, because I'm going to be doing this in some kind of loop. So I know I'm going to be doing this in some kind of loop. It's going to be for I. That's going to be the loop, and I'm going to be going around this a bunch of times, say n times. How many times is n? We're going to have to figure that out as well, but here we know basically how the calculation is going to work. I'm going to have some new value of x and v. I'm going to call those, I did this exactly backwards, right? Mistake number 1. It's part of the hiring the mentally handicapped system. X equals x new, v equals v new. So the old new is the new old, right? And so we move forward in time, and we're going to do this again and again, and it's going to tell us how we move forward. This is going to be our basic calculation. Now, to do this calculation, we're going to have to say, well, if I know the position and the time. Oh, by the way, how about the time? Time's going to move along too. So the time is going to equal the t new. And therefore, as I keep track of things, the new time is going to be the old time plus h. And that really tells you what h is. Okay? Now, my claim is that if I know the position, the velocity, and the time, I know the force. Well, how do I know it? It comes from the model of the mechanical system and the linear momentum balance, F equals ma. So the force is going to be some function of position and so on. So let me just do as my first example the harmonic oscillator. So it's going to be k times x. So we're going to do the harmonic oscillator as our equation. Okay, now I'm over and over again calculating these things, but probably I want to get some kind of plot. And here I've told MATLAB to calculate and be quiet, but I probably want to remember some of the things I'm calculating. So I'm going to have some array of the values of these things. And if I have an array going already, I can add to it the new value. So I have a new value of time, and I'm going to add that to an array. That means somewhere at the top here, I have to start initialize this array. I can initialize it with a single number, let's say the start time, which I didn't say what it is yet, but I'm going to have some start time for that. And then similarly, I'm going to have exactly the same command for position and velocity. I'll have an x array. That's going to be a storing of all the x numbers, and that's the old value of the x array, and add to it this new value of x. And then I'm going to have the same with the v array, all the values I have so far, and I'm going to add to that array a new value of this. So this is a concatenation. It's taking a list of numbers and making the list longer. Now, this is horrible MATLAB programming. Who knows, looking at this, like knows enough MATLAB to know that this is horrible programming? And most of you do not. Can somebody tell me why it's horrible MATLAB programming? Right, so see what's happened is that MATLAB has an array here, and I'm saying, okay, you remember that list of numbers? Now I'm going to make that list longer. But it's got to find some transistors to stuff that in, so it's got to find some new place in the computer to stuff a longer list, and then it does that. And every single time you add a number, it has to look around in the computer for some place to put that list of numbers. So the sort of professional way of doing this is to allocate space for this array ahead of time. But I'm not going to do that. There's lots of things here I'm not doing the professional way. I just want to show you the simple way so the concept is here. And then bit by bit, we will get more professional about it to make the code more efficient, more accurate, and so on. Okay, so we're going to leave it this bad way. It's bad in terms of running slowly in MATLAB, but computers are so fast now. You know, when I was a kid, your phones are more powerful than my computer was when I was your age. And that's true. Okay. So now we've got this list of numbers, but we have to initialize all of these arrays. So we have a v array, which is, sorry, I'd like to start with x array. And I'm going to initialize that with, say, the initial value of x. And I'm going to have a v array. And I'm going to initialize that with some initial value of v. Okay, so that means going up here to the top, I've got any problem where I'm going to predict the future, I've got to know where I start. In the world of differential equations, you call that initial conditions. So we've got to say, how are we starting this thing? We can't run our crystal ball. We can't predict the future of the universe without knowing where the universe is starting. So we have t is starting, t0 is some number. Usually, it's nice just to call 0, rather than when Jesus Christ was born. You just call it when the problem starts. And you say, what's x0? Let's do the simple harmonic oscillator problem. We do 1. Now, what do we mean by 1? So in any time when you go to the computer, you've got to be doing the problem in some consistent units. So make sure before you get to the computer that you're doing the whole thing in MKS, or foot-pound seconds, and you know the difference between a pound mass and a pound force, or grams and dynes and so on. You have to be using some consistent units. And then let's start out with some velocity 0, which is, say, 0. I'll get there. Okay, what else do we need? We need some material constants. So this is, remember, mechanics has 3 pillars in it. One of them is geometry, one of them is material properties, and one's the laws of mechanics. Clearly, we're going to use the laws of mechanics. Where are we going to use the laws of mechanics? We're going to use the laws of mechanics by we're going to write A is equal to F divided by M. There's the laws of mechanics right there. There's a linear momentum balance. So it's simple. The laws of mechanics are simple enough in this problem. And actually, the laws of mechanics are pretty simple in all problems. The hard parts of mechanics problems as we go along and setting them up are going to be in the kinematics. And here, in this problem, the kinematics happen to be simple. They're just this relationships between position, velocity, and acceleration. And then, as I was saying, we have the material properties, and those are here. So we see the 3 pillars of mechanics in this problem, like they are in all mechanics problems if you look carefully. All mechanics problems have these 3 ingredients. Anyway, going with these material properties, we've got to put in what the spring constant is, and 1 is a nice spring constant in some unit, like 1 Newton per meter, as opposed to 0.3011 and who knows what units over there. I think it might be newtons per centimeter, but I'm not sure. Pounds per inch, I don't know what they had in mind. And then it's not really material constant. It goes more with the laws of mechanics, but we can think of it as listed with the material constants. We have the mass of the system. So we've got some initial mass. Now let's just look and see if we've got a complete calculation. So we want to make sure that working our way down, we don't get to a place where anybody's confused. Okay, so we specify variables here, we specify variables here, we specify variables here. On the right-hand side, all of these are specified. For I equals 1 to n, oops, what's n? Well, what do we mean by n is how many times we want to go through this. Now, usually, people like to say how long they want to integrate rather than the number of integration steps. So let's say t1 equals some nice number. Now, a nice number, I like pi, and I like it a lot, so let's have 2 pi's. Okay, so this is going to be the final time for this model. So I want to predict the future up to a time of 2 pi. Okay. So now I've got the final time, but I still don't know what n is. So somewhere I have to calculate n. Well, I've decided how big the time steps are I'm going to take, and I know how much time I'm going to have, so I can calculate n. It's going to be the difference between t1 and the initial time, spelled with the letter 0, the number 0, not the number 0, and that tells me how many time steps I'm going to have. Okay. Okay, now I get to here, n is known. This is how many times we're going to go through this loop of predicting the future. Now the screen has gotten kind of cluttered. Let me tighten it up a little bit so you can see more stuff at one time. It's not very nice for printing things out, but it's a nice here in the lecture where I don't have a big enough screen. In fact, this is kind of not that interesting code anyway, so I can spread this out on one line. Remember, here's the laws of mechanics, and here is our crystal ball. So the core of this code is all in these lines here. Everything else is just helping this bit of code work. Yes? Do I need to move these lines down? Okay, so I don't know what x nu is yet, is the problem, right? On the other hand, if I move this line down, I'm not going to know what x is here. So I need to initialize this x nu, v nu, and so on, right? So up here where I specify my initial conditions, I need to make sure I've got those. So I need x nu is going to be equal to x0. That's to get things started. And I need v nu is equal to v0. And that's to get things started. And I need, and these are boring lines of code, so I'm not going to spread them out this way. And I also need t nu is equal to t0. And that's just to get, so bootstrapping is the thing to get us started, right? I need to initialize these variables. I'm not really using them very much. They're just to get started. Once I get in this loop, I'm going to be recycling these variables again and again. Yes? Say again? Does n need to be an integer? No, MATLAB is happy with this for some reason. It counts up to the lowest thing, but we can try that out. Let's see. What's 1 colon pi? Okay? Quick answer to your question. Any other question? Yes? Can you say that louder, please? Couldn't I use the same variable and just recycle it again and again here? So she says, why bother with this x new here? Why don't I just put t like this, x like this, v like this, and put t like this, and x like this, and this like this, and t like this, and won't everything be fine? Now I have two choices. I can go undo, 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 or I can say maybe this is okay. I think this is okay. Why didn't I write it like this? Is because I've got what in math land would be a ridiculous equation. This only makes sense in computer land, and I wrote it the other way because it makes sense in math land. The new variable is the old plus the rate times the change of time. Here I'm saying take the old one, get rid of it, and let's call it the new one. This saves some variables. I get to delete this whole line of code, and I make my code shorter, but the price I paid for that is that it's a little bit harder to understand. But since you already understand it, I'll take your suggestion. Does that address your question? Everybody understand her question and my answer? It's the difference between math land and computer land. It's an interesting thing about this equal sign. I first sort of got challenged by this when I tried to learn computer algebra, which you know in, say, Wolfram Alpha or Mathematica or Maple, so on, or Symbolic Toolbox in MATLAB. I started to learn it in a program called Maxima, which was sort of the grandfather of all these programs, the early 1980s. And this big book, okay, it's big like this, 3 volumes. The beginning of the book said, it should be recalled or realized that there are 7 different meanings for the equal sign. And I first read that and thought, they are just making this confusing. And then I realized, yes, there are 7 different meanings for the equal sign. When we write the equal sign, it's completely ambiguous. It has different meanings in different contexts, and that's confusing. So here, we've changed this equal sign from an identity to an assignment. We were using it ambiguously as both. Here, it only makes sense as an assignment. There are other meanings of the equal sign, too, which you can get into if you want to think about it. See if you can count to 7. OK. Now we've got the answer. Notice we have semicolon after everything, which means be quiet. So we want to get some results. So we can plot t and t array and x array. Okay. Now usually you get to this point and you run the program. It's not going to work. All those in favor of this working this time, raise your hands. All those opposed. Now I don't know, right? How could I know? I just typed this. I don't know what new mistakes I made, so I can't bet one way or another. I'm slightly in favor, you know, as a rule, I'd say 90%, 95% of the time I write a program about this long, it does not work. But now I feel like you've been checking me, so I feel like I have a good chance. Let's see how it goes. Incredible. Okay, so we predicted the future. We started here at 1. And we got this thing to oscillate. And does this look great or not great? Now, what's not great about it? It's got more energy at the end than at the beginning. So this is a bad crystal ball. So let's get a better crystal ball. Let's spend 10 times as much money for our crystal ball, and see if we spend 10 times as much money, we get a better crystal ball. Ah, isn't that cool? Okay, so it solved the equation just the way we want. Now, what you see here is this is not computer algebra. This is a numerical calculation. Nowhere hidden in here is the symbol sine function or cosine function. This is just predicting the future, following the rules, and calculating numerical values. It's a numerical solution. There's no hidden algebra of sines and cosines. It's not like in the background MATLAB is going, oh, I know that one. That's sine and cosine, and going and calculating and fooling. No, it's just doing arithmetic again and again, and it's getting this answer. Okay, now that we've got this, we can put in all kinds of different models. We can put in whatever model we want. So we can get rid of this model, and we can do the model for the cones following with the viscous drag. So the cones following, they fell according to the equation. It had an acceleration of m times g, and then it had a deceleration of c times v. And I'm doing the linear viscous cone just to keep it simple. Let's see, but I have to put some more material properties up here. I've got k. I've got to put a c equals 1. I've got to put a g. I'll make it 10, so it's pretty close to Earth's gravity. I like 10, by the way, not 9.8. Why is that? Because nothing else in your calculation is 2% accurate. Why bother to put a 9.8 instead of a 10? Okay. Unless you're doing some very precise calculation. 10 is good enough. Okay, so now I've got this, this problem. I can start this one off at 0 instead of at 1, and I can run this thing, and what do I get? I get exactly that plot I put on the blackboard at the last class. You start off at 0, then you accelerate, and eventually you reach terminal velocity. And this is position versus time, and this is just the plot I did on the blackboard. Any questions about this? Okay, now what if I want to do the problem that somebody proposed at the beginning of the class about sines and cosines and so on, and said, how come I drew that crazy graph when there was a sinusoidal forcing? So let's say the force was equal to cosine of t. What do we get for the position versus time? Okay, that worked out nice. Okay, let's do that for a longer time. So we can see, let's do 8 pi. See how it looks. Still looks pretty good. Hey, the amplitude's increasing a little bit. Let's spend 10 times as much money. You see what I did there? Any questions about what I did? If we're paying for computer time, I'm paying 10 times as much for computer time. I'm doing 10 times as many calculations, but then I'm taking smaller steps in the future, and my approximation of that, the new value of a function is the derivative times delta t plus the old, that linear approximation, that first term in the Taylor series, gets more and more accurate the smaller the time step I take. So 10 times more accurate, I made that more constant. Okay, that came out okay. What if instead I put here sine of t? Okay, you want to think about it for a minute? So the force is oscillating sinusoidally. The acceleration is oscillating sinusoidally. But by the time you've done one oscillation, you're more ahead than you were behind. You've got some average velocity. Now if I did just the right calculation, I could find the right initial velocity to straighten this down. Let me just try. I could put here -1. Now I'm just guessing wildly to try and straighten this out. Oh, that was good. So that was the right initial condition. But who asked the question about the cosine function? Do you see what's going on here? Okay, so it's true the acceleration is oscillating, but we don't know what the average velocity is. Okay, now we want to. Actually, there's another cool thing we can do here. Let's go back to the harmonic oscillator. Now that we've got a drag constant in here, we can also put minus c times v. What's that going to do to this oscillator? It becomes decaying oscillations. Let's say I don't like so much decay, make the decay less, run this again. It's decaying oscillations like that. What's the shape of this envelope here? Looks like it's sort of decaying linearly in time. well, let's see. Let's go for a longer time. Let's go 80 pi. Now, if we don't do a small, no, the h was fine. Let's just see how it goes. So you damp this thing out. It takes some while to calculate. Is it calculating, or does calculate, please? What happened? I put h was this. T1 is 80 times pi. Doesn't look like it accepted it very well, does it? Plot it. No, it's busy. It's busy again. I think it's doing all those things again and again, and it's forgetting to plot. Let me say, stop that, and stop that. Now let's try again. Let's let it think for a while. It's busy. See down here, busy. Why is it busy? Because I asked it to do a lot. Why is it going so slow? Is because of these lines here. That's what's making it go so incredibly slow. Still busy. Okay, so let me show you this MATLAB trickery then. We're going to say, let's see, the class ends at what? 11 o'clock, which is in 2 minutes. So be quiet. I'm not going to make this fix. What you should know, though, is that there are various things you can do to label this plot. For example, I can label this plot Andy's plot. Hang on a second. Shh. Look at your GPS official Greenwich clock time, and you will see that we've got a few seconds. Andy's plot, and I can say, I can do fancy things, like I can go font size 20 or 12 or 15, and I can make a big plot here with, let me go back here to my 2 pi. Okay, I made an error. That's the end of class. Okay, so you get the idea. Play around with plotting.